Alright, 9.7. Taylor polynomials, and we're going to use them to make approximations. Okay, so we're just going to go ahead and introduce you what this looks like. So here we go. Definition. If f has n derivatives, so we're going to go back to first semester. Derivatives are going to come in handy a lot here. At c, then the polynomial here we go, p subscript of n of x equals f of c plus f prime of c times x minus c plus f double prime of c over 2 factorial x minus c squared plus f triple prime factorial, over 3 factorial, times x minus c to the third power plus plus f of the n derivative, why do I keep saying factorial, of c over n factorial times x minus c to the n power. This is called nth Taylor polynomial for f at c. And I'll explain all this in just a second, so write it down. I'm going to go ahead and pause the video, copy down, and when you're ready, press play. If c equals to 0, he discovered that then p subscript of n of x would equal to f of 0 plus f prime of 0 x plus f double prime of 0 over 2 factorial x squared. What are you guys noticing? Isn't it technically the same thing? What's the difference? You're just plugging in 0, and when you think about it, you don't have this c value anymore because you're center at 0. So it's going to be end up being the same thing. So it's going to be all the way until you get to the nth derivative. So f of n. This guy's entire work was plugging in 0 to some other guy's function? Pretty much. Can I do that? I don't see why not. If you have that case where basically, in other words, if your center is 0, it's a special type of Taylor polynomial, and this guy stole the name, so it is called a Maclaurin polynomial. What a jerk. Cool? So it's technically the same thing. Exactly the same thing. It's just that your center will be 0. Okay? And you have a lot less to worry about. You don't have to be worrying about this x minus c because you have x minus 0. Okay? Alright, so we're going to go ahead and try our first example. We're going to find the nth Maclaurin polynomial for f of x equals e to the x. Right? Okay. Well, here's what we know. And you're going to have to do this for all these types of problems. We know that f of x equals e to the x, right? If you look at the formula that you have, this is depending on a whole bunch of derivatives. Agreed? So you're going to have to find a whole bunch of derivatives here. So what is the derivative of f of e to the x? E to the x. What is the double or the second derivative? E to the x. E to the x. So as you can see, we did something very, very simple. Yes, sir. Okay. All right. So sorry, I forgot to press record, so all of this is not going to make sense. So let me go ahead and rephrase what I said here. Once you figure out all of your derivatives and you evaluate them at 0 in this case, 0 in this case, because it's a Maclaurin polynomial, and the Maclaurin polynomial is going to be centered at 0, you're going to figure out that all of that is going to be equal to 1. So we're going to go back and use our formula. And literally you're plugging in f of 0, well, that's just 1. F prime of 0 was 1, so 1 times x. F double prime of 0 was 1 over 2 factorial times x squared, and so on, until you go to your nth term, which in our case would be what? 1 over n factorial times x to the n power. And that would be the nth Maclaurin polynomial for e to the x. So here's the interesting thing about Taylor polynomials and Maclaurin polynomials. Notice how the actual Maclaurin polynomial doesn't even have e to the x at all. And we can still use something that doesn't even have e to the x to approximate a value of, in this case, close to 0 of e to the x. How do we feel about this? Cool, like it's relatively simple. It's really plug and chug. Okay, so now let me show you how that would be used for approximations. So this would be in general. So now we're gonna use them to approximate something. Okay, so example number 2. We want to find a Taylor polynomial, and we're gonna do a couple of them. I want you to do a first degree Taylor polynomial, I want you to do a second degree Taylor polynomial, and I want you to do a third degree. So we're going to do 3 of them for the following. F of x equals natural log of x, and this is going to be centered at 1. Okay, so do you guys see why this one would not be a Maclaurin polynomial? So we're good. Okay, so because I'm going to have to do, I'm basically doing 3 problems at once, you tell me, where would you start? What do you need? So find the derivatives. How many derivatives are you going to have to take? 3. So I'm going to start with f of x is obviously natural log of x. First derivative of x would be what? 1 over x, right? Okay. Second derivative of ln of x will be, in this case, what? Negative 1 over x squared, right? Third derivative in this case would be what? 2 over x to the third power. We're good, right? We didn't forget how to derive. We're good? Okay. That's where you're going to stop this time, right? Because you know very specifically what type of, or what degree of polynomial you're looking for. Agreed? Now that you have the derivatives, what are you going to do? So evaluate each one of those at your c. So in this case, you need to find out what f of 1 is. So f of 1 in this case, natural log of 1 is 0. F prime of 1, so what is 1 over 1? 1. F double prime of 1 is going to be negative 1. Third derivative, evaluated at 1, is going to be 2. Agreed? Okay. So let's start with the first polynomial, a first degree polynomial, Taylor polynomial. How would that look like? So in this case, you don't want to use the n. You're actually going to put in the degree of polynomial that you have. So the first degree Taylor polynomial would be represented like this. And what would that one be equal to? So you're going to start with 0. And then what? Plus 1. And this one's look a little different because it's not centered at 0. So it's going to be x minus the center. So in this case, x minus 1 to the first power, right? And that's it. That's your first degree Taylor polynomial. If you simplify, that means it is just going to be x minus 1. Agreed? What would your second degree Taylor polynomial look like? So I still have the 0. I still have the 1 times x minus 1. So plus, and it's going to be a negative, right? Because it was negative 1. Right? So it's negative 1. over 2 factorial times x minus 1 squared. Cool? You don't need to simplify the factorials unless you really want to. Okay? I wouldn't. Because you're going to have a calculator for this. Okay? What will be your third degree Taylor polynomial? 0 plus, I'm going to start getting rid of some of this, x minus 1 plus, well, negative 1 over 2 factorial, x minus 1 squared plus what? We've already used the negative 1, so we're on to the next one. So 2 over what? 3 factorial times x minus 1 to the third power. Cool. Now here's what I want you to do. I want you to use all 3 examples that you have here. If this is centered at 1, let's find out what f of 1.1 would be equal to. Okay? So what would that be equal to? Use the 3. So you're going to have a calculator for this. Okay? So make sure you go ahead and grab your calculator if you don't have it. Alright, so let's start out with basically using our calculators and using the original function, right? So natural log of 1.1 is equal to that, right? So that's the actual natural log of 1.1, agreed? Now let's use the first degree polynomial to figure out if we get the same thing. So my first degree polynomial is x minus 1, right? So what is x? 1.1 minus 1. So here's what the approximation would give you of a first degree polynomial of the natural log of 1.1. Pretty close, right? Now what would happen if I use the second degree Taylor polynomial? So well, I have 1.1, right, minus 1 plus negative 1 over 2, if you go over to math, factorial times 1.1, so 0.1 square, right? And here's what I get. Now I got closer. You see that? So the higher degree Taylor polynomial that you have, the better and better approximation that you are going to get to the actual value of whatever you were trying to do, which in this case was the natural log of 1.1. We're good? Okay. Sweet. All right. Isn't that pretty nice? Like, it kind of blows my mind a little bit that you have like this is like not even close to a natural log, and I'm getting pretty much the same thing. Okay. Now here's the problem, that we have an approximation. We already did sort of approximations in this chapter, and we had to worry about the error. That's more than likely what I see the BC test asking you about a Taylor polynomial, the error. And we're going to talk about the error here in just a second. So I'm going to give you one more to practice like this, and then we'll talk about how do you take care of the error, or in other words, how close are you really to your approximation. Okay? Alright, so let's try another one. Find a Maclaurin polynomial of f of x equals cosine of x, and let's do this one. Let's do a 4th degree, and let's do a 6th degree Maclaurin polynomial. Okay? Obviously, which one's going to give you a better approximation? The 6th one, right? So let's try both of those. When you are done, I want you to use it to approximate f of 0.1. Okay? Check your work. Alright, so if you use your calculator here, where's my calculator? So cosine of 0.1, right? I got 0.999 0.50041653. Pretty good approximation, right? Yes, ma'am. The fourth? If you approximate it, like the fourth would be close to 7. So still pretty close, right? Cool. So I hope you're starting to see how powerful this Taylor polynomials can be. Okay? Alright, any questions before we move on to now? Let's talk about, obviously, because this is an approximation, there's gotta be a little error there. Alright, so let's figure out how to find out what that error is. Okay? So here we go. In order to do that, we're going to have to talk about something known as Taylor's theorem. Okay? So here's what Taylor's theorem says. It's a little confusing. So let's just first write it and then we'll talk about it. So Taylor's theorem. Bless you. Alright. So if a function f is differentiable through order, is this how you spell through? Yep, okay. Through order n plus 1 in an interval if a function f is differentiable through an order n plus 1 in an interval, and let's call that interval I, containing C. What is C again? It's going to be the center. Then, for each x in interval I, there exists z, so now I'm throwing in another variable here, z, between x and c, such that the following is true. F of x would be equal to f of c plus f prime c times x minus c plus f double prime c over 2 factorial times x minus c square plus dot 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 plus f to the n derivative at c over n factorial times x minus c to the n power plus, and here is a new addition to this polynomial now, r n of x. So look at it, it's the same thing as a Taylor polynomial with the exception that now you have this little thing here at the end. And I'll explain to you what this means here in just a second. So first write this down and then we can discuss a little bit further what all this means, because I think it's confusing. It's just the way that it's worded. It's kind of confusing, but it's really a simple concept. Okay? Let's talk about the definition because there's more to it, but let's pause at this point. And you're going to differentiate it just like we've been doing for all our Taylor polynomials. Here's the difference. It says that you got to be able to differentiate it through an order n. Notice how we did the nth degree Taylor degree polynomial, right? Well, what this is asking you to do is to take one more derivative. So do n plus 1, okay? So notice how the definition that we had earlier in the page was all the way up to here. But then we have a plus r's of n of x. And I'll explain to you what this means here in just a second. But also I want you to notice what this is. It says f of x. It no longer says p subscript of n of x, because that would make it a Taylor polynomial. And a Taylor polynomial gives you an approximation, right? So would you then agree that the Taylor polynomial would be from here to here? That would be your approximation. Agreed? So what do you think the r's of n of x represent? This is going to be the error. And I want you to think about it. If you have your approximation and you add the error, you should get the exact value of f of x. Okay? We're good? Well, here's the thing. There still has to be an error. It was probably a point, like the decimal kept going, but it was so small you couldn't see it with the calculator, but there's still going to be an error. Okay? So, the question then becomes, well, how do I figure out what this error is? Okay? And let me talk about what all of this means here on the interval. Okay? So, when you have an interval, this interval means, remember that you have a center, right? So remember how, like, on the last example, our center was 1? Or was it 0 for the last one? It was Maclaurin, right? So it was 0. And then I asked you to find out what point 1. Well, that's going to be your interval. 0 to point 1. Right? What this is telling you then is that in between there, in that interval, there's going to be a third value. We're going to call that value z. And we're going to need that value z for r's of n of x. And now I'm going to explain to you what this is. You ready? So here we go. Is equal to the n plus 1 derivative of the function, but at z, all over n plus 1 factorial times x minus c to the n plus 1 power. Well, that almost, if you look at that, isn't that exactly what everything else has been? You have the derivative, right? You have the factorial, you have the x minus c to the power, but the only difference and the most important thing is that this specifically is going to be evaluated not at the same value that you've been using. It's going to be evaluated at that z value, okay? And that's how you're going to determine that coefficient that would go in front of the x minus c n plus 1 over the n plus 1 factorial. We're good? So here's what that means. To make this simpler, remember how we were doing a 4th degree Taylor polynomial? If you're going to include the error, instead of taking 4 derivatives, take 5. Always do one more derivative. Okay? So here we go. Let's try one example. And this is the last thing we're doing pretty much today. So let's try it. The third Maclaurin polynomial for sine of x is the following. So you're not even finding it. There it is. It's given to you. You're going to use Taylor's theorem to approximate sine of point 1 and determine its accuracy. Cool? Alright. So it's given to you. So if we want to find the approximation, all we got to do is what? Plug it in, right? So third degree polynomial here of 0.1 is going to be equal to 0.1 minus 0.1 to the third power over 3 factorial. So use your calculator to find out what that would be. On this, remember how in this class we always round to 3? Let's not round to 3. This 3 will be too soon. Use as many decimals as it gives you as possible. Okay? So So 0.099833 repeating. Alright, so 33. We're good there. Okay? Good enough. Well, how accurate is this? Well, if you remember, I mean, you don't need to write this down. We said that f of x would be equal to your approximation plus that r. Agreed?
Yeah.
So we have our approximation. All we really need to figure out is this. Agreed? Well, how am I going to do that? Well, remember, what is this equal to? So the n plus 1 derivative of z over n plus 1 factorial times x minus c to the n plus 1, right? Well, we need to figure out what this z value is. Okay? But also, before I even get there, I'm going to need the n plus 1 derivative. So if I have the third degree polynomial, that means that I need the fourth derivative of, in this case, sine of x.
Yeah.
So you're going to have to end up doing that anyway. So if f of x is sine of x, f prime of x equals to cosine. F double prime would be negative sine. Third derivative, negative cosine. And the fourth derivative, positive sine. So it ended up being a trick for those. Repeat itself. Okay? Now that I have the fourth derivative, it says you're going to evaluate it at z. Okay. To figure out that z value, you want to use that interval. Well, what interval are we using here? Well, if you think about it, they gave you a Maclaurin polynomial, right? Which means that your center is 0. And they're asking you to evaluate this at 0.1, right? So your interval is going to be 0 to 0.1. Agreed? So there's got to be a value in between there, which we're going to pick for z. Now, you can pick anything for z that's in between there. Here is my advice to you. You want to pick the one that's going to give you the greatest error. Because if you pick something that's too small, you may underestimate the error, which would mean that you will not be as close as you think you are. So you want to have the greatest error. And the way to do that is to literally think about what would make this the greatest number. You can notice how I'm putting brackets, so you can actually end up using the 0 or the 0.1 as well. So you want to pick the number that's going to be in here. It's a closed interval that would make this to be the greatest. 0? What do you guys think? 0.1? Okay, I agree. 0.1. Why 0.1? Okay, well, let's talk about it. So let's look at this, okay? So let's say if we use a 0.1, that would mean that we would have r at 0.1, right? So that would be the fourth, or this derivative right here, at z. So sine of 0.1 is going to be greater than sine of 0. Agreed? Do you guys see where I'm going with this? So then that means that this is sine of 0.1, right? Over n plus 1 factorial. Well, what is n plus 1 factorial? What was our n? 4 factorial, right? Because look, we had 3 factorial, so the next one would be the 4 factorial. Times x minus c. Well, what was c? Well, 0, right? It was a Maclaurin, right? So we don't need that. So to the what power? To the 4, right? You guys with me? So here's my question, like you have everything except x, or do you have x? You do have x. What was x? So sine of 0.1 over 4 factorial times 0.1 to the 4th power, right? So whatever that is, I don't know what that is.
Pretty accurate.
What's the
4.160 times 10 to the
negative 7? Oh crap. So 1, 2, 3, 4, 5, 6, and then 4.
Yeah.
Right?
Yeah. Can you write that, or can you just write it down?
I don't think scientific. Right? Is this kind of what you guys got? You guys with me? So that means that, hey, in reality, where is sine of 0.1? Well, sine of 0.1 would definitely have to be greater than your approximation, right? So what was our approximation? 0.099833. It's greater than that, right? But it's got to be less than that plus your error. You guys with me? So what would 0.099833 plus your error be equal to? Try it on your calculator. I don't know what that would be. So take this number and add this number to it. Because remember, that's what it said, right? The theorem said if you take your approximation and you add your error, that's pretty like even closer to what your f of x is going to be, right? So your in this case, sine of 0.1 has to be greater than that, but it's got to be less than whatever that addition is. So 0.09983334, right? That's pretty darn close. And if you type sine of 0.1, you are going to get somewhere in between that. Cool? Bless you. That is going to be Taylor's theorem. Okay? The only other thing I can see them asking you with Taylor's theorem would be instead of actually finding the error, they'll tell you, hey, I want this error. What type of degree do I need to find? Or what degree polynomial would I need to find in order to achieve this type of error? Okay? We can do that if you guys like. Let's just go ahead and do that. We have time.
Yeah.
All right, we have plenty of time. So here we go. I'm actually surprised. We always run out of time. Here we go.
Well, we don't have null. Check it out. A little bit easier.
All right, so this is our last example of the day. We're going to determine the degree of the Maclaurin polynomial. No, I'm just to make it easier, just because they're centered at 0, but they don't have to. That should be used to approximate cosine of 0.1 so that the error is less than 0.001. So we're not doing one that's terrible, right? 0.001 is not going to be the greatest approximation, right? If I wanted something better, I could try like 0.00001 or something, right? Okay, so we're going to determine the degree of the Maclaurin polynomial so that we got a cosine of 0.1 so that the error is less than 0.001. Okay? Well, do you really need to find the Maclaurin polynomial for this? No, you only need that little error part of it, right? So let's refresh our memory. So here's what it means. So that means that f of x equals to cosine of x. Right? Which would mean that by the way, I forgot to mention it, the r really means the remainder. So the remainder of that polynomial has to be equal to the n plus 1 derivative of that function. Agreed? Over in that case, right? So here's what we know. Well, the n plus 1 derivative of x. Well, what would be the n plus 1 derivative of x? Right, so we're using cosine, right? So if we would do this again, that would be like the cosine sign, like this alternating between cosine and sine and cosine and sine and cosine and sine, right? And if it's Maclaurin, remember Maclaurin means that it's centered at 0, right? So that means that you're going to be, if you plug in 0, cosine of 0 is 1, sine of 0 is 0, right? And so you're going to have a lot of terms canceling out here and there, right? Now, what is your interval on this problem? 0 and 0.1 once again, right? Because it's centered at 0. Which one of those numbers would provide you with a better, if it's, remember, you're using the derivative, cosine of 0, which one will provide you with a higher number, cosine of 0 or cosine of 0.1? 0, because cosine of 0 is 1, right? You guys with me? So we're going to be using 0. So we're going to say that z is 0 for our case, okay? So if that's the case, it doesn't matter what derivative it is, right? It's going to be cosine of 0, which is 1, right? So then 1 times what? Well, you told me earlier, so it's n plus 1 factorial, right? Well, remember, it's the x. You have your x. What's your x? 0.1. To what power in this case? The n plus 1. And that has to be less than 0.001. Okay, let me make sure I did not lose anyone here. Remember that this is equal to f of n plus 1 of z, right, over n plus 1 factorial times x minus c to the n plus 1, right? So we just found out this right here. That's what we use as z value, right? And we said that the cosine of 0 is 1. That's where this 1 came from. Agreed? The n plus 1 factorial is there. And then the x minus c, well, if c is 0, so that's x minus 0, so it's just x. And your x was 0.1, so that's why it's 0.1 to the n plus 1 power. You guys with me? Now, so here's what you have, if you think about it. You have 0.1 to the n plus 1 over n plus 1 factorial has to be less than 0.001. What do you suggest? Yes, ma'am. No, because the z value determines, look, z is what you're going to be plugging into the derivative. Because this represents a derivative. So the derivative, the nth derivative for cosine was just the cosine. So the cosine of 0 gives you the 1. So there's the 1. You with me? So we're using the value that's going to give you the greatest value in here. Okay? Alright, so then how would you solve this, guys? What do you guys think? Well, you can try to cross multiply here, but then how do you get rid of a factorial if the other one doesn't have a factorial? And the answer to this is that algebraically this is impossible to solve. So you're going to have to play guess and check. So here's what I suggest you do. Here's what I did. I'm going to create a table where I start with 1 for n, 2, 3, and so on. And I'm going to use a calculator. Okay, so if you use 1, so try it. Plug in 1, so 1 plus 1 is 2. So try what that would give you on the calculator. So here's what I'm going to do because I'm lazy. I'm going to store the value. So 0.1 store, 0.1 store in x. And I'm going to type the expression exactly how it looks. So alpha y equals enter. So 0.1 to the x plus 1 power over x plus 1 factorial. Right? So here's what I got. Oh, what did I do? Oh, I put 0.1 instead of 1. I'm sorry. Good. So I got 0.005. So that's definitely not less than that, right? So I gotta keep going. So now I'm gonna try 2. So 2 store in x. So second enter. And I got 0.0001, right? So 0.00016. As you can see at this point, is this number less than that? Definitely is. Therefore, n would have to be 2, which means that you have to find a second degree Maclaurin polynomial in order to get an error that is less than 0.001. Yes, sir. Well, you're looking for at least, like, with this ones, let me ask you something. Like, with this ones, it can be very tedious. Like, the longer they are, the more you have to do, right? So you want to find the smallest one possible that still fits within that range. So I would say just n equals 2. But I agree, n equals 3 would also work, n equals 4. But the first one that would work would be a second degree one. Okay? Alright, that's all I got for you today, guys.